So let's consider a circuit where we have some phasor voltage source Vs like so. Here is some resistance R. And then we have this coil here. I'm going to put the dot up here, and I'm going to say that it has N1 turns. And then down here below it, we have a second coil having N2 turns. And these two coils are perfectly coupled together. Then over here on the right-hand side, I'm going to connect my load impedance like so. I'm going to define my primary voltage V1 as the voltage drop across those two coils. And I'm going to define my secondary voltage V2 as the voltage drop across just that bottommost coil. So let me explain a little bit about what's going on physically in this system. I believe I mentioned this at the end of our last class meeting, but an auto transformer is a transformer that utilizes a tapped single coil to perform a voltage transformation operation. So effectively, if we wind a coil, let me draw a picture over here. So if we had, for simplicity's sake, a cylindrical core like so, and we wrapped, bless you, a wire around it, we've formed just a single coil like we've been dealing with. But there's nothing stopping us from effectively tapping this coil, which means we're just connecting another section of wire that gives us access to some intermediate point in the whole coil. Now, we may not realize it, but we actually see this literally every single day in our homes. So the secondary side of the transformer that feeds your home is an example of a tapped coil where between these two outside wires, that's where we get the 240 volts RMS that supplies power to large appliances like our ovens, hot water heaters, and things like that. But that is a center tapped coil. So meaning that the coil is split exactly in two. So if we measure from either of the outside terminals to the center, that's where the 120 volts that we use to power most of our smaller electronics, microwaves, television, computers, and all that kind of stuff, that's where that comes from. Well, this is a similar situation, but instead of being the secondary side of a conventional transformer, this is in and of itself a transformer. So if this coil has N1 turns and this coil has N2 turns, the whole thing has N is equal to N1 plus N2 turns.
So what you're saying is, in the example you just described, you can also get 240 volt and 120 volt from one coil.
Yes.
It's like you just have the dual functionality.
So in our homes, we get effectively plus or minus 120 volts as well as 240 off of the secondary side of the step-down transformer that connects the substation to our home. So if you were to crack open your breaker panel, the real name for that is what's called a load center, but if you were to crack that bad boy open, you would actually see that there are 3 buses inside. So you have a bus connected to this guy right here, a neutral bus, and then a bus connected to this guy right here. And so an individual circuit breaker would be connected either between here and here or here and here. So on the left-hand side, giving you access to positive 120 volts RMS. On the right-hand side, giving you access to effectively negative 120 volts RMS, but they're effectively the same thing because most of our modern electronic devices don't really care about positive and negative polarity terminals for AC things. But anyway, if you have something that's occupying two breaker slots, it's actually connecting from here to here, and then that's how it's giving you the 240. So it's connecting on the outside edge. If you look at the inside of a load center, like the bus work and all that kind of stuff is really interesting because it forms this weird zigzaggy shape, but it's just so that the blades or the breaker blades can just clip in exactly to where they need to be to make it as compact as possible. But effectively, you just have one bus associated with the high side, or this top terminal, one with the low terminal, and then a neutral in the middle. Okay. So we've got effectively a single coil that we've split up into two different smaller coils. We're taking our primary to be the voltage across the entirety of the coil, and our secondary as the voltage across just a portion of the coil. And so let's see effectively how that shakes out in terms of our transformer quantities like turns ratio and how that relates to both how we can step up or step down voltage, as well as step up or step down current. So I'm going to define my primary and secondary currents as follows. So my primary current, I1, is the current flowing here. My secondary current, I2, is the current flowing out through my load. And so if we define our voltage, our induced voltage V2, we should get something like this, right? So we have a self term, which is just going to be J omega L2. So that's the impedance of the secondary coil here. What's the total current flowing through that secondary coil? I1 minus I2 according to Kirchhoff's current law, right? So if I1 is flowing in and I2 is flowing out, then we have to have a current of I1 minus I2 flowing out as well in order for KCL to be satisfied. So let me just sneak that in here really quickly. So we'll have I1 minus I2 plus J omega M times I1. Once again, we can use the relationship that M is simply A times L1, which we derived in class on Friday. So that's going to give us, oh, and L2 is A squared times L1. So we're going to have J omega A squared L1 times I1 minus I2 plus J omega A L1 times I1, and factoring out J omega A L1, we'll be left with an I1 from the second term plus A times I1 minus I2 from the first term. For our voltage V1, we are going to have the voltage drop from here to here. So that's across this first coil. And then added to that will simply be V2, because V2 is the potential difference from here to here. So this V1 in total is the voltage drop across the coil having N1 turns plus the V2 that we already found. Are we okay with that application of KVL? Okay. So that should look like J omega L1 times I1 plus J omega M times I1 minus I2 plus V2. So that's going to give us J omega L1 I1 plus J omega A L1 I1 minus I2 plus J omega A L1 times I1 plus A I1 minus I2. And now everything is in terms of L1, I1, and I2. So we can lump things together. So we could pull out a factor of J omega L, leaving us with I1, L1, I1 plus A I1 minus I2 plus J omega A L1 times I1 plus A I1 minus I2, or J omega L times 1 plus A I1 plus A I1 minus I2. Are we okay with our algebra here and how I've moved things around? So effectively, the left-hand side is the exact same thing as the right-hand side, except a factor of A. So we just have 1 plus A, J omega L1, and then the bit in the brackets. Okay, so from this, we could say that, V2 over V1 would just be 1, right? So if we look at V2, we've got a J omega A L1 times this bit in the brackets. When we look at V1, we've got a J omega L times 1 plus A times this bit in the brackets. So this L1 right here, I'm sorry, I'll fix that in a second. This J omega L1 cancels this J omega L1. This bit in the brackets cancels this bit in the brackets. And all we're left with is A over 1 plus A, where A is defined to be N2 over N1 over 1 plus N2 over N1. And if we multiply through by a factor of N1 over N1, that leaves us with N2 divided by N1 plus N2, or simply N2 divided by N, where N, once again, is just the total number of turns in the large coil. We should see that the ratio of our currents is nothing more than the inverse of the ratio of our voltages, or N1 plus N2 divided by N2, which could be simply written as N over N2. And I got that second result there for the currents just by using the fact that energy in or power in has to equal power out. So if we are stepping down the voltage by a particular amount, should be stepping up the current by the opposite. So if I were trying to reflect my impedance ZL from the secondary side over to the primary side, what would I need to do?
Solve your I2.
So when we had our simple original transformer and we were reflecting from the secondary to the primary, what did we do? Divided by the turns ratio squared. Well, this guy right here is playing the role of the turns ratio for this system, right? So I think, and I might decide to make you guys prove it as part of an assignment, maybe even a test question. I'm that much of a jerk. That we can simply divide our load impedance by this quantity squared to reflect it over to the primary. So such that our impedance ZL prime should just be ZL divided by N2 over N1 plus N2 squared, which is the same thing as ZL times N1 plus N2 over N2 squared. Again, that can be derived pretty easily, but we're not bothering with that because we went through the derivation steps of how to do it for our simple transformer. And this is just a specialized case of the exact same thing. So now let's look at a step up auto transformer, right? So we had a step down here.
When you say reflected to the primary side, you mean what?
What does the voltage, what impedance does our voltage source VS see? Just like what we did on Friday. So our voltage source VS would see this impedance multiplied by N1 plus N2 over N2 squared, and from the terminals between here and here, right? So let me.
Okay, so that includes.
Exactly right. Can we look at, excuse me, step up auto transformers now? We good copying this stuff down? Okay. So for a step up auto transformer, we're effectively going to have the same thing, except that our secondary voltage is going to be defined as across over the entire coil, and our primary voltage is just going to be over a portion of the coil. Okay, so something akin to this. So here's our voltage Vs, our resistance R, actually, let me flip that bad boy over so that I can draw the lines correctly. like so. So this will be V2 and I2. This will be V1. And here's our current I1, like so. So how would we define the voltage V1 for this guy? Positive polarity terminal is at the dot. Current's flowing, what's the current flowing into the dotted terminal? I1 minus I2. So we would have J omega L2 times I1 minus I2 as our self term.
Is there a reason why that wire at the bottom is spaced between the dot?
Is that what you're talking about?
Yeah.
No, I just, oh, why does it erase it? That's literally even worse.
Okay.
I'm just trying to give you a terminal so that you know where the transformer starts. So that's
All right, that's fine.
all right. So for our mutual thing, right? Positive polarity is at the dot. Our current I2 is flowing into the undotted portion of coil labeled with N1. So that should give me minus J omega M I2. And now we can simply substitute things in. So that'll be J omega A squared L1 times I1 minus I2 minus J omega A L1 times I2, factoring out a J omega A L1, we are left with A I1 minus I2 minus I2, like so. V2 is once again similar to how we calculated V1 in the last example. So it's the voltage drop across this coil plus this voltage V1 according to Kirchhoff's voltage law. So if I'm looking at the voltage drop across just this coil right here, or I'm assuming we're going to go plus, minus, so that they just add directly. The positive polarity terminal of voltage drop across this coil labeled as N1 is at the dot. The current is flowing into the undotted terminal, so I should have a negative sign on my self-induced term. So that's going to look like negative J omega L1 I2 Again, positive polarity is at the dot. The current that's flowing into this dot is just I1 minus I2. So we'll have plus J omega M I1 minus I2. And then we'll simply add to this our voltage V1 from our previous step. Once again, we can simply substitute things in. So this is going to give us negative J omega L1 I2 plus J omega A L1 times I1 minus I2 plus J omega A L1 times A I1 minus I2 minus I2. And now we're gonna lump stuff together, right? So I can pull out a common factor of j omega L1 for my first two terms. That's going to leave behind an A I1 minus I2 from my second term minus I2 from my first term plus j omega A L1 times A I1 minus I2 minus I2 like so. And this leaves us with the first term, it's j omega L1. The second term is j omega AL1. So I'm going to pull out a common factor of 1 plus A. Like so. And from here, we can see that the turns ratio, as it were, for this step up auto transformer is going to be 1 plus A over A. Or 1 plus N2 over N1 divided by N2 over N1 comes out to be N1 plus N2 over N2, or N over N2. Our current I2 over I1 is just the reciprocal of our voltage relationship. So that is N2 over N1 plus N2, or N2 over N. And lastly, if we were to reflect our impedance Z1, excuse me, ZL over from the secondary side to the primary side, that winds up becoming ZL times N2 over N1 plus N2, excuse me. Squared. Yes.
Is this the same thing like when you said A is the reciprocal of what we're doing?
Should be the exact same thing. Yep. So let's talk very briefly about the fundamental differences between the transformer that we looked at on Friday, where we had two isolated coils and an auto transformer here. So both of them are very regularly used in the power industry, but they're used for different things. Okay. So the transformer where we have two completely separate coils, there is no physical connection between them. We can think of that as what's called an isolation transformer, where effectively we want to make sure that there is separation between any signals on those lines. So that happens very regularly in the case of things where we're designing like audio amplifiers and all of that kind of stuff. And as a matter of fact, the first design problem for this class, most of you guys should be well aware by this point that I am a huge guitar nerd and all of that kind of good stuff. Anybody else in here play guitar? How many of you guys have an amplifier? Okay. Do you have like a head or do you have a combo? So like a head would be literally just an amplifier head that you connect to a speaker cabinet and all of that kind of stuff. Whereas a combo has all of that integrated into one package. So anybody with like a half stack or a full stack or anything like that, Nobody's just completely rocking out and pissing off their neighbors or anything? Okay, whatever. You guys are way too nice. So usually when you have a guitar head or something like that, it can plug up into a variety of different speaker cabinets, okay? So depending on if you're using like a 2x12 combo, that might have one particular impedance, might be 16 ohms. If you have a 4x12 combo, that might have an impedance of 8 ohms. And if you have two 4x12 cabinets wired together, that might look like 4 ohms, just because of the way that it's wired. So effectively, your amplifier head has to be able to connect to an impedance of either 4 ohms, 8 ohms, or 16 ohms without causing any damage to the head. You guys haven't learned any transmission line theory or anything like that just yet. You will by the end of this year, because your junior year is just gross and brutal. But anyway, effectively, one of the things that you'll learn later on is that if you don't have the impedance of your load matched to the impedance of your, the input impedance of your load matched to the output impedance of your amplifier, you can get reflections and standing waves and all of this kind of stuff that can damage sensitive electronics. So how they let an amplifier be usable by multiple different types of speaker cabinets is by including a transformer that has multiple tap points so that we can make that impedance of the speaker cabinet look like different things depending on where it's connected. So the output impedance of a transistor-based amplifier might be 10 kiloohms. And so you need to be able to make that 10 kiloohms look like 16, 8, 4, possibly 2, but I don't think they do that much anymore. So that's what your first design project is designing a multi-tapped isolation transformer that looks like either 16 ohms, depending on where you connect it, or 8 ohms, depending on where you connect it, or 4 ohms, depending on where you connect it. So that's isolation transformers. You'll see that in a lot of electronic equipment. For these auto transformers, there is no isolation between the two coils because there isn't two coils. There's just one coil that's split up. So you'll see auto transformers used a whole heck of a lot in substations because you want the smallest possible footprint for all of that large equipment. Now, I will say an auto transformer is typically significantly more expensive than a conventional isolation transformer because all of the wire has to be able to carry the largest amount of current that's ever going to flow through that thing. So instead of just one side being able to carry a lot of current, the whole thing has to be designed to carry a lot of current. More copper equals more money. All right, so let's see. Let's run through three-phase transformers relatively quickly, and then I think that'll be enough for today before we get into gross convolution integrals. So I could not find my notes, so I just brought my textbook here really quickly. But for the most part, we can think of a three-phase transformer as simply three single-phase transformers like we've dealt with previously that are wired together in a particular configuration. For better or for worse, and this is actually for better even though it looks gross, we have three different options for three-phase transformers, right? So we can go from Y on the primary side to Y on the secondary side. We can go from delta on the primary side to delta on the secondary side, or we can go from Y on one side to delta on the other side. Those delta Y transformers are what are used in substations as well, because typically you use a delta connected system for transmitting over long distances, and then you step down to a Y because that's what we're typically used to, is having access to a neutral. So if we look at a YY transformer, it might look something like this. So let me slap a terminal over here. So I'm going to call this A1 and I'm going to call this terminal over here A2. So this is the A phase of the primary on the left-hand side and the A phase of the secondary on the right-hand side. So the subscript is denoting whether or not we're on the primary side of the transformer or the secondary side of the transformer. And the letters are telling us which phase we're on. So let's call this guy right here B1. This is our neutral one. And then let's see, how do I make this the least gross as possible? So this will be C2. This will be C1. This will be B2, like so. So I've got all my coils. I'm going to define my turns ratio as N1 to N2, like so. And
Is there a neutral too or not?
there is. Let me use lowercase n, or that's going to get rather confusing. Thank you for that. So this voltage that I have defined over here is just the magnitude of our line voltages on the primary side. So VL for line voltage, because I'm measuring from transmission line terminal to transmission line terminal, just to refresh you guys that it's been a hot minute since you took circuits 2. Here is our line current for our primary side. Here is our line current for our secondary side. And here will be VL2. And I'm going to explicitly put magnitudes here. Like so, just because I don't want this diagram to get ridiculously busy. And really all that we're going to care about is the magnitudes, because we hopefully all know at this point that in a balanced 3-phase system, if we know what's going on in the A phase, then the B phase is just 120 degrees lagging, and the C phase is just 240 degrees lagging. So for our voltages, the magnitude of VL2 is just going to be N2 over N1 times the magnitude of VL1. And the magnitude of IL2 is just going to be N1 over N2 times the magnitude of IL1. So there's our YY transformer in terms of line voltages and currents. If for whatever reason we wanted phase voltages and currents, well, we know that this would be the same and our phase voltages would just be divided by, or excuse me, to get phase voltages from line voltages, we just divide these by root 3. Now, let's look at our delta delta. So here will be A1 terminal. Once again, this is the A phase on the primary side. So something like that. Here's the B phase on our primary side. Let me jump this over. Actually, let me move that guy over even more. Put the dot here. Yep, thank you for that. Just a simple mistake. Oh, Jesus. These things are so gross and annoying to draw and have them make a damn bit of sense. And I'm sure you guys are thinking to yourself, they don't make any sense. What the hell is he talking about? And that's okay. All right. So we've got this giant monstrosity here. It's probably a little wider than it needs to be, but that'll be okay. Here's A2, C2, and B2. So let me just make sure everything is okay. So effectively, just as a quick heads up, we define the dot as away from the neutral on all of these. So I wanted to make sure here that the dots effectively cycle through. So it should go like dot, not dot, dot, not dot, dot, not dot, and so on and so forth. So that seems to be all okay there. Everything looks to be wired up. So let's go ahead and define our voltages. So once again, this will be the magnitude of VL1 and the magnitude of IL1 flowing in. This will be the magnitude of VL2 and the magnitude of IL2 flowing out. And our relationship for voltages and current should be literally the exact same thing as we had a moment ago. So the magnitude of VL2 should be N2 over N1. Actually, let me write the turns ratio here. So N1 to N2 of VL1, and IL2 should be N1 over N2 IL1. Lastly, we have our Y to delta. I'm going to draw this as if the Y connection is the primary and the delta connection is the secondary, but it could be the opposite. So literally you would just replace every subscript 1 with 2 and vice versa if you wanted it to go the other direction. Okay. So here is a Y delta 3-phase transformer. So I'm going to start by drawing my coils and then I'm going to work from there. All right, so over here, I'm going to put the neutral of my primary side, and there is not going to be a neutral on my secondary because it's a delta configuration. I'm trying to make that look like it's jumping over and not just the letter C. So all of my neutrals are connected together, excuse me, which should make sense. Let's put C1 here. Like so. Let's put B1 here. And A1 here. And so I believe, unless I've made a mistake that I don't obviously see, we can see that the primary coil here is between the A and the neutral. This guy is between the B and the neutral, and this guy is between the C and the neutral, exactly like what we should expect. Once again, the dots are on the side away from the neutral, the common neutral conductor. So we're good there. Then we've got to wire up our delta. So we just draw some legs on this bad boy. Crap. So this is going to be A2. And we should see that our C phase transformer and our A phase transformer are touching this like so. Here is B2. And then lastly, crap. Here is C2. Like so. All right, so if I define my line voltage magnitude here, so this will be the magnitude of VL1 and This will be the magnitude of VL2. Then we have the relationship that, let me just put it exactly how it's written in the book so I don't screw this up. VL1 over VL2 magnitude is equal to our turns ratio, which is N2 over N1. So let me define that really quickly. So here's N1, here's N2 over the square root of 3. And for our currents, so here will be IL1 magnitude. Here will be IL2 magnitude. We have oh, son of a bitch, my bad. It should probably be flowing out of as well, but it doesn't matter because we're only dealing with the magnitudes. I just realized I got these mixed up. Secondary should be on top, primary should be on bottom for it to be N2 over N1 divided by root 3. And then here we have IL2 over IL1. And this should be root 3 times N1 over N2. There we go. Just the inverse. Okay, so those are the 3 different types of 3-phase configurations that you may see. And for those of you that go get an internship at, Entergy, Clico, AEP, that kind of thing, chances are you'll wind up dealing with literally all of them. Yes, Isaiah, how may I help you?
So since the C and N1 terminals, VL1, we gotta define, go to that last.
That's actually, that's wrong. I'm sorry. It shouldn't be between the neutral and C. It should be between A and B or B and C. So thank you for pointing that out because that is very much a mistake. Because I want a line voltage and not a phase voltage as I had just described it. So thank you for pointing that out, Isaiah. Just a mistake on my part. All right, so we have finished talking about transformers in regards to this particular class. For those of you that are more interested in it, you have the opportunity in the fall quarter of your senior year to take a course called Electric Machinery and Power Electronics, where you will start off going in great detail about transformers, how they operate, and then actually what you're going to learn is that the equivalent circuit for most electrical, rotating electrical machinery, so induction motors, synchronous motors and generators and all that kind of stuff, actually looks like a transformer. In fact, the electrically equivalent circuit for an induction motor is just a transformer that you allow the secondary to rotate. It is the same effective circuit. David, how may I help you? So square root of 3 divided by N2 over N1 is the same thing as square root of 3 multiplied by N1 over N2. Yes. So if we, maybe an easier way to write this would be N2 over root 3 N1, so that we see the current is the same thing, just flipped over, because that's all it's supposed to be. Thank you for that. All right. So anyway, like I was saying, for those of you that are interested in all that kind of stuff, there are classes that do, Dr. Batari does a much better job of explaining this stuff than I do, I am damn sure. For what it's worth, how many of you guys have heard about the Fundamentals of Engineering exam or getting a PE license? All right, so almost all of you guys. Great. So in electrical engineering, your PE license is typically either you get it in power or you get it in controls or you get it in every other thing related to electrical engineering. Dr. Batari teaches our power series of courses. So that is ELEN 484 in the fall, ELEN 481 in the winter, and ELEN something in the spring. And I say something because he likes to make up new classes just based on what his research is. So it's always power related. Anyway, he would probably be embarrassed to hear me tell you guys this or brag on him. But so far, over the past 3 or 4 years, our electrical engineering students that have passed their FE exam and go on to take the power PE exam, 100% of them have passed it on their first try. So whatever he's doing, he is doing a fantastic job at preparing our graduates for getting their PE and electrical engineering. So if you're interested in power and all of that kind of good stuff, you couldn't be in better hands than Prashana Batari. All right, so that is enough ranting out of me for today. So on Wednesday, we are going to get bogged down in some really gross math. I'm sure you guys are thrilled.